Hello everybody, and welcome to our video on trigonometric equations. So, solving a trigonometric equation means finding a set of solutions, not just one. And that should be pretty natural because a statement like sine of x equals 1, for example, has the solution x equals pi over 2, but it also has the solution of 5 pi over 2, so forth and so on. So there's many x values you could plug in that would correspond to the same output. So in fact, trigonometric equations often have infinitely many solutions. So we're going to start out by taking a look at some basic forms of equations and some basic key facts that we need. And then we'll take those and apply those to solving more general equations. So to start, for any integer n, sine of theta equals 0 if and only if theta equals n times pi. This is pretty straightforward. If we just sketch the unit circle real quick here. We see on the unit circle there are immediately two angles that obviously correspond to a y value of 0. And that's going to be the angle 0 and the angle pi. So sine of theta equals 0 when theta is 0 or pi. But of course, if you went another pi, you'd get sine of 0 again, so 2 pi. And if you went backwards by pi, that's negative pi, and so forth and so on. So what we see here is that theta can actually be described as all integer multiples of pi. Now, on the other hand, when we consider the question of cosine of theta being equal to 0, well, it's very similar. But the first angle where cosine is equal to 0 is at pi over 2. And the next one is down here at 3 pi over 2. But of course, what do we see here? If you go from pi over 2 to 3 pi over 2, you're really adding pi. And we could add pi again and end up back where we started. That would be 5 pi over 2. Or we could have subtracted pi. We could have gone backwards by half of a circle. And in any case, all of those angles will correspond to values where cosine of theta is 0. So we can describe this a little more simply by saying that this is pi over 2 plus any integer multiple of pi. Now for tangent of theta equals to 0, of course tangent of theta is equal to sine of theta divided by cosine of theta. So tangent of theta is 0 whenever sine of theta is 0. So it has the same solution set as sine of theta equals 0 here. Now, another thing that we want to take a close look at here, the following three facts are going to be very helpful for understanding our general solutions to our trigonometric equations. So this first fact here is sine of pi minus theta equals sine of theta. So if we just draw, we'll just draw the top half of the unit circle for ease here. That'll be enough to get the picture. So if I have an angle theta, then the y value here is, of course, sine of theta. So what I want to find is an angle that has the same y value as sine of theta. And I maybe could have drawn that a little bit better. That's really more here. Well, that's easy enough. We'll just draw a straight line across here. Look, where's the same y value? That's this point here. And since these are mirror images, this angle is also going to be theta. So the angle from the positive x-axis is pi minus theta. So all we're saying here is that when I draw the angle theta, and I draw the angle pi minus theta, they have the same y value. So in other words, sine of pi minus theta and sine of theta are equal to one another. Okay, so now let's take a look at cosine of theta here. So this one's a little different. So because sine of theta is describing the y values, when we look for the angle that has the same y value, we have to look for a mirror image over the y-axis. But cosine is talking about the x values on the unit circle, right? So here we need to look for something that's a mirror image over the x-axis. So we draw our unit circle again. Again, rough sketch, doesn't have to be perfect. So this is theta. So we want to have the same cosine value, right? So we need to figure out which angle gives us that. Well, since this is a mirror image over the x-axis, this angle is the minus theta here. So that means that my angle from the positive x-axis is 2 pi minus theta, as if you went the full circle and then subtracted theta. So cosine of 2 pi minus theta is equal to cosine of theta. That's all we're saying here, that when we look at this picture, that this angle theta gives you the same x value that you get for the angle 2 pi minus theta. Now lastly, for tangent, we've got tangent of pi plus theta equals tangent of theta. So here I've got the angle theta. Now remember, tangent of theta is y divided by x when we look at our coordinates here. So here, when we add pi, where do we end up? Well, we end up at the mirror image across into the third quadrant. So it's over the y-axis, then over the x-axis. So what do we get for our coordinates? We get negative x, negative y. So in this case, tangent of pi plus theta is negative y over negative x, but those negatives cancel, so it's the same thing as y over x. So in other words, tangent of theta and tangent of pi plus theta are equal. Okay, so that's a lot of time to spend on this symmetry for the unit circle, just to really reinforce the point of how we're going to approach finding our solutions in general. Because if we understand these relationships, it actually saves us quite a bit of time at figuring out our general equations. So using these facts, what we're going to do is apply one of the three sets of solutions to equations of the form sine of x equals sine of alpha, cosine of x equals cosine of alpha, or tangent of x equals tangent of alpha. So, here's the key thing. If we can write an equation in the form sine of x equals sine of alpha, of course, when x equals alpha, these two things will be equal, right? If x was alpha, you would just say, hey, these are equal. But we also know that if alpha is a solution, then pi minus alpha is a solution based on this symmetry. And we also know that for each of these angles, anytime you get a solution, so anytime you have some angle that is a solution to the equation, then if I just add 2 pi, I end up at the same point on the unit circle, so that should also solve the equation. So here we're just saying, if alpha is a solution, so is pi minus alpha, and so is any angle where you've just added a multiple of 2 pi. That's like spinning around a full circle on the unit circle again, or backwards. Okay, so let's go ahead and tackle an actual problem with this. Now, remember, we're going to stick to radians for these examples for the most part, but you can always apply this to an equation written in terms of degrees by just, instead of writing pi in your solutions, replace it with 180 degrees. Works exactly the same way. Okay, so find all solutions to sine of x equals the square root of 3 over 2. So our goal here is always going to be to get our equation into one of these 3 forms, or in the simpler cases, we can turn it into one of these: sine of theta equals 0, cosine of theta equals 0, tangent of theta equals 0. Those are the simpler cases, but generally speaking, we want to write it in this way. So I ask myself, what angle gives me the square root of 3 over 2 for sine of x? Okay, well, if I'm a little rusty, I might draw it out a little. Oh, that's here. Oh, that looks like pi over 3. So sine of x equals sine of pi over 3. That's all we're saying here. This is the same statement. Square root of 3 over 2 is sine of pi over 3. So sine of x being equal to square root of 3 over 2 is the same thing as saying sine of x equals sine of pi over 3. I know I'm taking my time with that. I just want to be as clear about it as possible. Now that we've got this equation, sine of x equals sine of alpha, our solutions come in 2 forms. X equals alpha, in this case pi over 3, right? Plus any 2 pi times n multiple. And our solutions come in the form pi minus alpha plus any multiple of 2 pi. So now we just have to simplify a little bit. So this first equation is fine. There's nothing to simplify. Now our second equation, we've got pi minus pi thirds. That's 3 pi over 3 minus 1 pi over 3. That's 2 pi over 3 plus 2 pi times n. So all solutions to this equation are written in this form. Okay, so let's go ahead and move on to another equation. So here we have tangent of x equals negative root 3 over 3. Now in this case, we've got this tangent of x equals tangent of alpha equation, and all solutions here come in the form x equals alpha plus n times pi. Now this is the special case here, and this comes back to this picture we drew earlier. There's only one equation set for tangent because the second solution in the unit circle is exactly pi away, which means we can write all of our solutions as just a multiple of pi instead of being 2 sets of solutions that are multiples of 2 pi, right? When we look at this picture for sine, this angle and this angle here, they've got like an odd distance between them. So we have to describe all the solutions generated from the green being rotated separately from all the solutions being generated from the blue. But in the case of tangent, since the first and second solution are exactly pi apart, then we can just keep adding multiples of pi and simplify it, right? So we're just simplifying the case here. So the trick here is figuring out what that angle is. Tangent of x equals tangent of alpha. What is alpha? Well, for these problems, I don't expect anyone to have all of the values for tangent memorized. That doesn't really make much sense. So instead, let's kind of think of it like this. We want to know what tangent of alpha is, right? What is alpha? So let's think of it as sine of alpha over cosine of alpha equals negative root 3 over 3. And then we can just think about what values for sine and cosine would give us this. So I need a negative one and a positive one. Now, since the first quadrant both would be positive and the second quadrant cosine would be negative, I'll make cosine my negative term here. So I got to think about, combinations of sine and cosine that happen together. Like maybe square root of 3 over 2 and 1/2, but negative. Well, when I simplify this, I would get negative root 3, which is not the same thing, right? So that doesn't work. That's okay. Try something else. So root 3 over 2 and negative 1/2 didn't work. Let's try 1/2 and negative root 3 over 2. Well, the 2's cancel, and I get negative 1 over root 3, which if I rationalize this would be exactly the same thing that we have here. So that tells me, oh, that's the angle. That's the one I need. So what is alpha then? Well, sine needs to be 1/2, and cosine needs to be negative root 3 over 2. So that would be the angle 5 pi over 6. So now I can rewrite my equation as tangent of x equals tangent of 5 pi over 6. And that tells me all solutions come in the form 5 pi over 6 plus an integer multiple of pi. So again, tangent is the nice one where all of its solutions come in the one equation. That's just a multiple of a single pi, and as opposed to the 2 pi multiple. Okay, so let's go ahead and apply this to a problem that's a little more complicated, just requires a little more algebra. It's not bad. Find all solutions to the equation in the interval 0 to 2 pi. So this is a little trickier because now, instead of just finding all of the solutions, we have to restrict our solutions to just being between 0 and 2 pi. But we're basically going to start this in the same exact way. So the first goal, and this is the key thing to keep in mind, your first goal is to get everything into one of these three forms. So here our goal is to write this as cosine of x equals cosine of alpha. So I'm going to start out by isolating the cosine to one side of the equation. So if I subtract the 1, I get 2 times cosine of x minus pi over 4 equals negative 1. And then I divide by 2, I get cosine of x minus pi over 4 equals negative 1/2. And now I ask myself, what angle for cosine gives me negative 1/2? So that would be what's got to be in the second quadrant, and that's going to be 2 pi thirds. So cosine of x minus pi over 4 equals cosine of 2 pi thirds. Okay, now we can approach our solutions in exactly the same way, but just keep in mind, now what's inside the left-hand side isn't just x, it's x minus pi over 4. So when we write our solutions, we don't write x equals, we write x minus pi over 4 equals, right? So we get two sets of equations, x minus pi over 4 equals 2 pi thirds plus any 2 pi multiple of an integer, and x minus pi over 4 equals 2 pi minus 2 pi thirds. Again, gotta keep track of a lot of little details here. Since we're dealing with cosine, and cosine is symmetric over the x-axis, that's why this angle needs to be 2 pi minus 2 pi thirds. Okay, so now we just need to go through a little bit of simplification here for each of these equations. So I'll start by adding pi over 4 to both sides here. Get 2 pi thirds plus pi over 4 plus my 2 pi integer multiples. And in here, I really need two different steps to get to the same place. So first thing I'm going to do is rewrite 2 pi as 6 pi over 3 so that I can subtract these. That gives me x minus pi over 4 equals 4 pi thirds plus 2 pi n. And now I'm going to add my pi over 4 to the other side. So I get 4 pi thirds plus pi over 4 plus 2 pi times n. And now I need to simplify these a little bit further and just combine these standalone constant terms here. So I'm going to look for a common denominator, and that's going to be 12, right? So what do we get here? This is going to be times 4 over 4. And this one I've got to multiply by 3 over 3. So this is going to give me 8 pi over 12 plus 3 pi over 12 plus 2 pi n. And keep in mind, we're not trying to include this term right now because this is a multiple of n, which is a variable in this case. So we don't want to try to combine that with our constant terms. It's just going to make things simpler for us later on. Now similarly over here, but we're going to get 16 pi over 12 for our first term when finding our common denominator. And here we're going to get 3 pi over 12. Okay, now let's go a little quicker. 8 pi over 12 plus 3 pi over 12, that's 11 pi over 12 plus 2 pi times n. And this is 19 pi over 12 plus 2 pi times n. Okay, so this is, if we were asking for all possible solutions, these would be all possible solutions. But we're not asking for all possible solutions. We're asking for all solutions just in the interval from 0 to 2 pi. Now, for the most part, this basically just comes down to plug and chug. Just check, plug in values for n, see what you get. But in this case, it's really simple. So in this example, if I plug in n equals 0, I just get 11 pi over 12. And I need to check, is 11 pi over 12 between 0 and 2 pi? Sure, it's positive, and it's smaller than pi, so it's certainly smaller than 2 pi. Now, if I was to check n equals 1, in this case, it's pretty obvious that that's not going to work, because if I take a positive number and I add 2 pi, then I'm going to get something bigger than 2 pi. So that one's not going to work. And if I was to try to plug in n equals negative 1, I would get 11 pi over 12 minus 2 pi. But of course, that's going to be smaller than 0. So that's not going to work. So we've got one solution from this equation. And then when we look over here, we do the same reasoning. Plug in n equals 0. Now when we plug in n equals 1, I'd be adding 2 pi to a positive number. That's going to be bigger than 2 pi. That's not going to work. When I plug in n equals negative 1, I'd be subtracting 2 pi from something smaller than 2 pi. That's going to be negative, so that's not going to work. So that means all of my solutions from 0 to 2 pi are just 11 pi over 12 and 19 pi over 12. So just to clarify a little bit further, I don't need to plug in anything bigger than 1 here, because once I saw that this didn't work, I knew that if I kept adding larger numbers, I would still be bigger than 2 pi. And I didn't need to plug in smaller values for n, because once I got a negative result, I knew I would keep getting negative results if I used smaller values for n. So that allowed me to just stop there. Now, the other question that one might ask is, well, it's kind of obvious here that just these two angles are going to be the ones for the solutions. And that's true in this particular equation. We'll get a little bit further, and we'll get into situations either involving tangent or double angles in the next section, where that's not always the case. So I want to start the habit of actually plugging in multiple n values, or at least mentally checking, even if I'm not really calculating it, I'm still thinking about this number plus 2 pi, that's bigger. I'm proactively thinking about it, so that when I get to the stage where I really do need to actively check those things, I'm not just brushing it off, right? So that's the big picture here. Okay, let's go ahead and move on to the next problem. So find all solutions to the equation secant of x equals 2 over square root of 2. Now, this typically is something that I find trips students up a lot, but really it just comes back to the same thing that we said before, which is our goal. Our goal is to write our equation in one of these three forms. Sine of x equals sine of alpha, cosine of x equals cosine of alpha, or tangent of x equals tangent of alpha. So if you've got secant, cosecant, or cotangent, then your strategy should just be to rewrite it in terms of your other trig functions. So going back to this problem, we know that secant of x is 1 over cosine of x. That's the same exact thing as secant of x, so just wrote that as 1 over cosine of x. And so now if I take the reciprocal of both sides of the equation, I get cosine of x over 1 equals the square root of 2 over 2. But I don't need to write cosine of x over 1, that's redundant. So we'll just leave that as cosine of x equals the square root of 2 over 2. And then I just ask myself, what angle gives me the square root of 2 over 2 for cosine? And pi over 4 does, so that'll work. That gives me two sets of solutions here. X equals pi over 4 plus any multiple of 2 pi. And x equals 2 pi minus pi over 4 plus any multiple of 2 pi. And 2 pi minus pi over 4, well, that's 8 pi over 4 minus 1 pi over 4. That's 7 pi over 4. So all solutions to this equation will be in the form of these two equations themselves. Okay, let's move on to another example. So here, this is something a little bit tougher. I wouldn't call it tough, but it's tougher. So here, we have to use what's called the zero product property from algebra. So in this equation, we've got 2 times cosine of x plus 1 multiplied by square root of 3 times tangent of x minus 1 equals 0. So recall that if a times b equals 0, then a equals 0 or b equals 0, right? The only way a product can be equal to 0 is if one of the two things that you're multiplying together is 0. And that's true here as well. You're multiplying each of these things in parentheses, you're getting 0. So this implies that either 2 cosine of x plus 1 equals 0, or the square root of 3 times tangent of x minus 1 equals 0. Okay, so this first one, we'll just subtract 1 and divide by 2, and we get cosine of x equals -1/2. And we can rewrite that as cosine of x equals cosine of 2 pi thirds. Because 2 pi thirds is the angle that gives me -1/2 for cosine. Now for this tangent one, we'll add 1 and divide by the square root of 2. Or sorry, the square root of 3, I meant to say. And again, we're going to think about that as sine of x over cosine of x equals 1 over root 3. And what would give me 1 over radical 3? Well, 1/2 divided by the square root of 3 over 2. That would simplify to give me 1 over radical 3. So then what angle should I use here? So if sine is 1/2, that would be pi over 6. So then we'll rewrite this equation as tangent of x equals tangent of pi over 6. Now for the cosine equation, we get two sets of solutions. X equals 2 pi thirds plus any 2 pi integer multiple. And x equals 2 pi minus 2 pi thirds plus any integer multiple of 2 pi. And then for tangent, remember we only get one equation of solutions for tangent. That's going to be the angle, pi over 6, plus any pi multiple of n. Now I do need to simplify this a little bit here. X equals 2 pi minus 2 pi thirds. That's 6 pi thirds minus 2 pi thirds. That's 4 pi thirds. So altogether we have three equations that we have to consider here. And we need to restrict ourselves to between 0 and 2 pi, as those are the angles that were specified in the problem. So we're going to break our groups of answers up into three. So the first here, well, when n equals 0, we just get 2 pi thirds. If n was 1, I'd be adding 2 pi. That would be too big. If n was -1, I would be subtracting 2 pi. That would give me a negative value, so that doesn't work. Now over here, when n is 0, we get 4 pi thirds. When n is 1, we get 4 pi thirds plus 2 pi. That's going to be larger than 2 pi. That's too big. And when n is -1, we'd be subtracting 2 pi. That's going to be less than 0. That's going to be too small. So that's two solutions so far. And now we look at tangent. So when n equals 0, we get pi over 6. But when n equals 1, we get pi over 6 plus pi. So that's 7 pi over 6. Now if n was equal to 2, I would be adding 2 pi. That would be too big. And if n was equal to -1, I would get a negative value here. So altogether, we get 4 solutions. And it's not necessary, but I'm going to write these in order of smallest to largest. So this tangent one is an example where we actually need to plug in multiple n values. And again, this is still just a simple case. It can get more complex than this, but it's good to just check, find your first solutions, check in each direction until you get something that fails, and then you know you can stop. Okay, one last problem in this section. So this one, I would say, is a little bit more on the tricky side compared to other problems. Find all solutions to the equation in the interval from 0 to 2 pi. So before we tackle this one, I just want to have a little bit of an aside to get thinking about something before it comes up. And this is the idea of extraneous solutions. So let's take a really simple example here. The equation x minus 1 equals 0. Now, there's only one solution to this equation, and that's x equals 1. So there's one solution here. Now, sometimes in attempting to solve an equation, we might choose to square both sides of the equation. So, in this case, if x minus 1 equals 0, then x minus 1 squared equals 0. Hold on, that's not exactly the example I want to use. Let me try that again. Instead, we want to look at this equation, x equals 1, right? So x equals 1 has one solution, right? But if I square both sides, that should still be true. But if x squared is equal to 1, there's actually two values of x that solve this equation. So x could be 1 or negative 1. So that's two solutions. So the point being that in the process of squaring this, we actually introduce an extra solution that isn't part of the original equation. So this is called an extraneous solution, because although it does solve the new equation, it's not part of the original equation that we squared to get here. Now, why is that relevant? Well, the technique we're going to have to use to solve this equation is going to introduce an extraneous solution. So we have to actually deal with that. So we have tangent of x plus 1 equals secant of x. And so in order to solve this, we're actually going to want to apply Pythagorean identities. You know, the tangent squared of x plus 1 equals secant squared of x, which obviously does not work here because these terms are not squared. So what we're going to do is square both sides of the equation. So we get tangent of x plus 1 squared equals secant of x squared. So when we square the left-hand side, we get tangent squared of x plus 2 times tangent of x plus 1 equals secant of x squared. And now I can use my Pythagorean identity here to replace secant squared of x with tangent squared of x plus 1. So now what do we notice? Well, we can subtract tangent squared of x from both sides of the equation and 1 from both sides of the equation. And that gives us 2 times tangent of x equals 0. But that's the same thing as saying tangent of x equals 0. And we know that all solutions for tangent of x equals 0 are just multiples of pi. Now, it says find all solutions in 0 to 2 pi. So in 0 to 2 pi, the potential solutions are x equals 0 or x equals pi. But notice, when we looked at these two solutions, if I plugged in negative 1 into this equation, I would get negative 1 equals 1, which is absurd. So the only way to check which of the solutions we got might be extraneous is to plug into the original equation. Plugging it into the new equation doesn't check anything. -1 squared is equal to 1. We have to plug it into the original equation. So we check tangent of x plus 1 equals secant of x. And we'll start with x equals 0. Well, tangent of 0 equals 0. And 1 plus secant of 0 equals 1 plus 1 over cosine of 0. Cosine of 0 is 1. Oops, I did forget a little something here. That left hand, I wrote this incorrectly. I put my 1 in the wrong place. My bad. Let's fix that. Sorry for any confusion there. Okay. Left-hand side is tangent of x plus 1. So this should have been tangent of 0 plus 1, which is equal to 0 plus 1, which is 1. Now the right-hand side is secant of x. So we plug in 0. That's 1 over cosine of 0, which is 1 divided by 1. Are these two things equal? Yes, they are. So x equals 0 is a solution. Now we check x equals pi. Well, tangent of pi is 0. So the left-hand side of the equation does give us 1. Now we check secant of pi. Well, that's 1 over cosine of pi. But cosine of pi is -1. So this is 1 divided by -1, which is -1. So these are not equal. So the only solution is x equals 0. Okay, so that was a little bit of a long one, but hopefully that wasn't too much. So again, I do want to reiterate though, keep in mind that our goal for all of these problems boils down to either finding these really simple solutions, these simple equations, where it's sine, cosine, or tangent equals 0, or rewriting your equation in this form: sine of x equals sine of alpha, cosine of x equals cosine of alpha, or tangent of x equals tangent of alpha. As long as you focus on that, the rest is pretty straightforward. It's just the algebra gets a little messy sometimes, so make sure you're careful with that. All right, that's it for this one. Thank you for watching.